All right, so now we're going to talk about what we call conditional probability. So here, let me give an example. Let's say we draw two cards from a deck of 52 without replacement. Find the probability that the first is a heart and the second card is a heart. All right, so let's label some events here. Let's let A be the event that the first card is a heart, B the event that the second card is a heart. And one thing to note here is that the probability the second card is a heart is affected by the first card. Why? Well, two reasons. Number one, there's now only 51 cards in the deck, right? If you pick a card first. And number two, your first card was a heart, so that you have fewer hearts in the deck, right? You only have 3 left. This is what we mean by a conditional probability. This probability of B is affected by what happened on your first draw. Okay. Now the way we do this, if we want the probability of A and B, so we want the probability of A and the probability of B, we're going to multiply those together, right? They're two things that happen. But notation-wise, it's not just the probability of A times the probability of B. We're going to call this the probability of B given A. Okay, this is a conditional probability here, right? The probability of B on the condition that A already happened. Okay, we picked a heart on our first draw. So probability of A happening, your first card is a heart. There's 13 out of 52 hearts in the deck. But for your second probability, there's only 12 hearts left since your first one was a heart, and there's also only 51 cards left in the deck. So that's why those probabilities are not the same, and we multiply them together. If you reduce the fractions, it makes it a little bit easier. 13 out of 52 is 1/4, and it happens that 12 out of 51 is 4 out of 17, so the 4's cancel. One way we could describe B is its probability is dependent on A, right? Depends on what happened with A, whether you picked a heart or not, right? This would have been different if you didn't pick a heart on your first card. Okay. Now, what if the first card was, okay, we've been talking a lot about like replacement and not replacement, like, you know, even with marbles pulling out of a jar, if you pull them out and replace them, then that's different than if you just pull them out. Same thing with cards. If the first card was replaced back into the deck, well then the probability of A and B, let's move this up here. There we go. The probability of A and B really would just be the probability that first card was a heart is 13 out of 52, and because you put it back, you still have 13 hearts and 52 cards in the deck. You would just multiply those together. That's 1/4 times 1/4 is 1/16. In this situation, B's probability is, we call this independent of A's occurrence, meaning it doesn't matter what happened with A because you're putting the card back, so you still have the same sample space. More about independence coming up. Okay. So our general formula, as we saw used in the first example, if you want to find the probability of A and B, it's the probability of A times the probability of B given A. Now, we know it doesn't really matter how you label events. One's A, the other's B. So if you labeled it the other way, if B happens first, then it would be the probability of B times the probability of A given B. It doesn't really matter. Now, if we manipulate either this equation or this one with that, we can find a general formula for the probability of either A given B or probability of B given A. Let's use this one because this one's right here. If I solve for the probability of B given A, I would just divide the probability of A and B by the probability of A. And if it was the other way around, it's the probability of A and B over the probability of B. So we have a formula for a conditional probability question. That being said, what I will tell you is sometimes it's easier to not use that formula, in my opinion. Okay. It exists, which is actually nice. We're going to need those formulas going forward. So let me show you what I mean. Let's say we have one card drawn from a deck of 52. We want to find the probability that it is a queen, given that we knew we drew a face card. Okay. And this is a characteristic of a conditional probability, is that you know some additional information. It's not just the probability to pick a queen. Ooh, we already know that we picked a face card, right? So we have a higher chance that it is a queen, right? Because face cards are jack, queens, and kings. So method one, here I'm just going to do them side to side, and we'll talk about the differences here. Okay. Method one, which doesn't involve using the formula, is to just look at the reduced sample space. The reduced sample space is this. If we already knew we picked a face card, there's no need to consider all the other cards in the deck other than face cards. So notation-wise, you can write this as omega sub b, the face cards. I've got all 12 of my possible face cards. And of these 12 face cards, how many are queens? Well, there are 4 of them. So the probability that we got a queen, given that we picked a face card, is these 4 queens out of these 12 face cards, which comes out to be 1/3. Now, if we want to use the formula that we just talked about, then we do want to use the entire sample space, not the reduced sample space. So the probability of A given B is the probability of A and B divided by the probability of B. What's the probability of A and B? That's the probability of getting both a queen and a face card. There's 4 of those, right? It's a queen and a face card, so it's these guys right there. And then divide that by the probability of B, which is all of your face cards, which is 12 out of 52. And of course, the 52s cancel. We get the same answer. So it is nice we have choices. You can use the formula, or you can think about the reduced sample space. Okay, and here's another one. Let's say we pick a card. We want to find the probability that it is a heart, given that it is a 7. If you look at the reduced sample space, we would only consider, we already know we picked a 7, so we have 4 7s, right? A 7 of hearts, 7 diamonds, 7 of clubs, 7 of spades. The probability that we picked a heart, which is this one, given that we picked a 7, would be this one out of the 4 total. Very simple. If we use the formula, the probability of A given B is the probability of both getting a heart and a 7, meaning the 7 of hearts, so that's 1 out of 52. Divide that by the probability that we got a 7, which is 4 out of 52. And of course, that reduces to 1/4 as well. How about the probability that we get a king, given that it is a club that we drew? So if you want to pause the video and see if you can work out that probability either way, either using the reduced sample space or the formula. Okay, so here's my solution. If we use the reduced sample space, then we would only be considering clubs, because we knew that was the suit we picked. There's all 13 of those. And the probability that we got a king is that 1 king out of the 13 clubs, 1 out of 13. Using the formula, the probability that I got both a king and a club is the king of clubs, 1 out of 52, divided by the probability of getting a club, which was 13 out of 52, same answer. Okay, enough of the cards here. How about this? A family has 2 children. One of them is a girl. Find the probability that both are girls. Again, the way you spot this as a conditional probability is we know something already, right? We know that one of them is a girl already, so that has ruled out. We know this family did not have boy, right? we know one of them is a girl already, then that reduces our sample space to the number of ways of having two children where one of them is a girl, right? And so we only have 3 here, right? Boy, boy is missing. And I labeled them just to show you it doesn't matter, right? This one came first, so I labeled that A, I labeled this B. So it's really the probability of B given A. But it doesn't matter, right? What's the probability that are both girls? It's this one out of the 3, so 1/3. Using the formula, the probability that you get one is a girl and both are girls would be this one out of, remember here we would have to use the entire sample space, right? So we'd have to consider, let's write that in. We would have to consider the entire sample space, which is boy, 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 girl, girl, boy, girl, girl. So when we say 1, we're only talking about this one here out of the entire sample space, which is 4. And then divide that by the probability where 1 is a girl, which is the 3 out of the 4. That gives me 1/3. Okay. Similar question, but a little different. Let's say the family has 2 children, a different family, and we know the youngest is a girl. And so we want to find the probability that the oldest is also a girl. Okay, it's a little different question if you think about it, right? Because this is specifying that the youngest one was a girl, not just one was a girl. The youngest was a girl. Let's use the formula here. So my entire sample space is sitting right here. The probability of B given A is the probability that A and B both happen, that the youngest is a girl and the oldest is a girl, divided by the probability that the youngest is a girl. Okay, both of them, youngest and oldest is a girl, is this 1 out of the 4. Youngest is a girl. Okay, we're looking at the last one if you think about it, right? Because the firstborn is the oldest, the second one is the youngest, so that would be this one and this one. So these 2 out of 4. And that gives you 1/2. Now something to note here is the probability of B given A right here, this 1/2, really is, if you think about it, that's just the same as the probability of B. In other words, if someone just said a family had 2 children, find the probability that the oldest is a girl, you would have written out these 4 entries in your sample space, and the oldest being a girl would have been the firstborn. That would have been these 2, right? And that's 1/2 as well, right? That's 2/4, which is exactly what came out as the probability of B given A. Now, if you think about it, that makes perfect sense. The probability that the oldest is a girl doesn't depend on whether the youngest was a girl or not, right? Probability that the second child is a girl is 1/2, right? It doesn't matter what happens first. So in this case, A's occurrence had no effect on B's probability. And then I wrote a little thing here. Yeah, intuitively would know that would be true. Even if the first child was a girl, the probability of the second being a girl is still going to be 1/2. And this gets more specific to the idea of what we mean about 2 events being independent. When 2 events are independent, for example, the probability of A given B is just the probability of A. It wouldn't matter what happened if B happened. Or the other way, probability of B given A is equal to the probability of B. Now, if you go back to the formula for 2 things happening together, the intersection, that would mean if 2 events were independent, the probability of A intersect B is just simply the probability of A times the probability of B. Examples of independent events are what you would probably think of. Flipping coins. When you flip a coin 2 times in a row, what happens on the second flip doesn't matter what happened on the first flip. Having children, as we just saw. Rolling dice. When you roll a dice multiple times, it doesn't remember what happened the previous time. That has no influence on the current roll. Okay. And that idea of independence does come into play when you get questions like this. Say you have a multiple choice question with five possible answers. 10 questions, A, B, C, D, or E. Let's find the probability if you randomly guessed of getting all 10 correct. And the assumption here is that if you're randomly guessing, whatever you answer for the question before has no influence. It doesn't affect how you're going to answer the next question. Okay, so there's this assumption of each answer being independent of another. Okay. And if the events are independent, then you can think of each question as a blank in your multiplication principle. Calculate the probability that the first is correct, which is 1/5, and just times that by the probability the second is correct, which is also 1/5, third is correct, all the way to the 10th question. So this would come out to be 1/5 to the 10th power, which is extremely small, as you probably would imagine. You're not gonna, if you randomly guess on 10 questions, there's a very low likelihood that you're gonna get all of them correct. Well, what about the probability of getting 9 correct? Right? Maybe that should be higher. What you have to consider here is ways of getting 9 correct. It could be that you got the first one wrong and all of the rest correct, or the second one wrong and the remaining ones correct, or the third one wrong, or the fourth one wrong, or the fifth one wrong, or the last one wrong. All of these are situations of getting 9 questions correct, and so we would find those probabilities and add them together. Probability of the first one is wrong is 4 out of 5, and then the probability that the remaining 9 are correct is 1/5 times 1/5 times 1/5, 9 times. For the second one being wrong, first one's right, so that's a 1/5 probability. Second one is wrong is 4/5, and then the remaining questions are 1/5 probability. And you can kind of see what happens. The 4/5 moves over each time until you get to the last scenario, which is getting the first 9 correct and the last one wrong. Now, if you think about it, all of these are the same probabilities. You have 1/4 and you have 1/5 to the 9th. For this one, for all of them. So what we really have is 10 times 4/5 times 1/5 to the 9th. And another way to think of this, because this is going to help us with our next question, why 10? Because we wanted to consider all of the ways of getting 1 question out of the 10 questions correct, right? So it's a combination. And then they will all have a 4/5 and a 1/5 to the 9th. That is also a very low probability, albeit a little bit higher than trying to get all 10 correct. Let's extend it. What about getting at least 8 correct? Which is the number of ways of getting 8 correct and 2 wrong, or 9 correct and 1 wrong, or all 10 correct. So here we're doing at least, right? So we're adding those probabilities. Borrowing what we did here, we just did this right here on the previous problem, 9 correct. Counting the ways of getting the probability of getting 8 correct, you first want to count the number of ways of getting 2 of them wrong, or 8 correct, doesn't matter, but 2 of them wrong out of the 10 questions. And then if you think of your 10 questions, 2 of them will have a 4/5 probability of getting them wrong, and 8 of them will have a 1/5 chance of getting them right. So you'd have 4/5 squared, 1/5 to the 8th. And then you would add it to this answer plus the one we did at the beginning, which I just put this in lightly. You can see that the pattern would follow here, right? It's the same. 4/5 to the 0 is 1, 10 choose 0 is also 1. And that comes out to be also a very, very small answer. This idea here is also referred to as the binomial probability, a binomial probability. Some of you might be hearing those terms in class. Okay. Last question here, but it's a big one. Let's say you're a doctor. After you get your degree, you're going to be a doctor, and you might be giving your patients diagnostic tests to detect diseases. And so, as many of you are probably aware, many disease tests are not perfect, and some of them produce false positives and false negatives. And so we're going to explore what happens to a disease test that has a certain percentage of false positives and false negatives, and what that means in terms of probabilities a patient has a disease. So let's say for this particular test, 98% of the time when the person actually has the disease, the test will correctly identify it. But also realize that means 2% of the time it won't, okay? So that would be a false negative. That means 2% of the time, someone is going to think they have the disease, but the blood test doesn't say they do. So they're going to think they don't have it, right? So that's a dangerous thing. Also, this blood test gives a positive result 6% of the time when the person doesn't have the disease, what's called a false positive. And that's not ideal as well, right? Because then patients are now worrying that they have a disease when in fact they don't. Let's assume that the prevalence of the disease is 1 out of 250 people. So the question is, if the random person takes this test, what is the probability they will test positive? Okay, so let's, just to make the calculations a little bit easier, let's let A represent a positive test result. B is the event that the person has the disease, so of course B complement means they don't have the disease. Now, one thing we'll note here is that positive test results can come from people who have the disease, of course, but also ones who don't have the disease. And so if we're asked to find the probability of A, the probability of a positive test result, that could happen 2 ways. And so you see what I've done here. A tree branch diagram is a good way to model a probability that could happen in a couple of different ways, or more than one different way. So along this branch, these are people who have the disease. Probability the person has the disease is 1 out of 250. Now, the 98% is a conditional probability. That's the probability they get a positive test result given that they have the disease, which is 0.98. And we would multiply those together and get this small decimal. But we also get positive test results. I could put or positive test results from people who don't have the disease, which is 249 out of 250 people, times that by the probability they get a positive test result, given that they don't have the disease, which is 6%, multiply those together, and that gives me this decimal. So the total probability of getting a positive test result, you would add these two together, and it's 0.0638, which is relatively low. Nevertheless, okay, put yourself in the doctor's position. If your patient got a positive test result, they would still be a little bit worried, right? That they have the disease. So what would you advise as a doctor? I know what I would do. I would advise them to take the test again, right? Because assuming the tests are independent, the probability that a person tests positive twice without having the disease, you would expect to be very, very low. And in fact, it is very, very low. So let's assume the blood tests are independent. I think that's a safe assumption. The first test result has no effect on the second one. The probability that the person tests positive twice, which I'm going to label as 2A. Again, that can come from people who have the disease or people who don't have the disease. So I got 1 over 250. Probability they test twice. Probability they test positive the first time was 0.98, and the second time, assuming it's independent, is also 0.98. So it'd be 0.98 squared. And that gives me this decimal. Also include the people who don't have the disease, 249 out of 250. Positive test result given that they have the disease is 0.06 times 0.06, which gives me this decimal. So the probability that anybody tests positive twice on this test is very, very small, right? That's less than 1%. Nevertheless, and we're going to talk about this on the next video, just because a person tests positive twice, they may have the disease or they may not. So the big question we want to know is, if your patient tests positive twice, what's the probability they have the disease? And kind of a clue to that answer, what I want you to think about is, let's go back to the first one. This was the overall probability of a person testing positive once. But if you think about how this number is formed, it's formed from this decimal and this decimal. These are people who have the disease, and these are people who don't have the disease, right? Hopefully you can see that the majority of this number comes from the people who don't have the disease, right? So if you test positive once, it's very likely you're coming from this group rather than this group, the people who have the disease, okay? But if you look at the numbers when a person tests positive twice, this is your overall probability, but notice how is it split between the people who have the disease and the people who don't have the disease. Notice it's split rather evenly, right? So this overall number, I would say, is more closer to probably 50% chance that it either came from somebody who has the disease or didn't have the disease, right? So it's a much higher chance that you fall into the group of having the disease if you test positive twice. And again, on the next video, we will actually compute that probability.